should be a review for you as well. Some of you more so than others, but NMR is an important component in instrumental analysis and organic chemistry. And in my opinion, it's more powerful than IR. IR puts you in a general category. NMR will allow you, with proper interpretation, to actually identify the compound. And so we're going to go through that again fairly quickly here. NMR is based on the phenomenon of resonating nuclei that are magnetically susceptible. In order to be magnetically susceptible, the nucleus has to have an odd number of protons or neutrons or both. Some examples, common examples that we can use in NMR are standard hydrogen, sometimes called protium, carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. All of these have an odd number of particles present in the nucleus, which allows them or makes them magnetically susceptible, which means I put them in a magnetic field and they respond to the field if it's strong enough. Okay? So what we're looking at here is a nucleus that's magnetically susceptible, and if it's got this characteristic, when it's spinning, it creates its own magnetic field. Okay, and there's something called the right-hand rule, you've maybe heard before, that if the nucleus is spinning in the direction of your fingers when you're sort of forming a fist with your right hand, the north will be the thumb. Okay, and so you can actually envision it in that fashion. And this happens with an electromagnet as well. I simply run electric current around a pole, a piece of metal, and I can actually magnetize that and create an electromagnet. Same thing is happening with a nucleus that's magnetically susceptible. Now, if I apply a strong magnetic field to a small magnet like the nucleus, it will align itself with or against that magnetic field. There are two alignment states. One of them is called alpha, one of them is called beta, and in fact this slide is mislabeled. This lower energy form should actually be aligned with the magnetic field. I'm not real sure what they were intending. This end should be up there and this should be down here probably. Nevertheless, when the lower energy state, the little spinning nucleus aligns itself with the magnetic field, the higher energy state, the beta state, it lines itself against. And so don't pay any attention to this particular slide. I'm not real sure who proved it that they didn't prove it correct.
That's what's in the book.
It's that way in the book too?
Should the N and the S on both the second one and the third one be switched?
Generally, when we draw the applied magnetic field, the arrow points north. Okay. And so it looks like this, to me, has been mislabeled. Okay, and so, but I don't know. Who can get into the mind of the graphic artist that was creating this? So. But that's how it's supposed to be, and you'll see, I think, in subsequent slides it is.
The higher energy state is when they're opposite, right?
The higher energy state is when they're opposed to the magnetic field. Okay, and so here we've got, this is correctly labeled. Here's our applied magnetic field, and you can see that our nucleus is spinning or precessing in harmony or in sync with the higher, the applied field. Here, it's opposed. That's not too complicated, right? No. The difference in energy between these two spin states is very small. And so what we'll end up doing is striking those nuclei with electromagnetic radiation of very low energy, and they'll start to resonate back and forth between the two states. But it has to be the right energy. So here we have a number of hydrogen, and let's use hydrogen as an example, hydrogen atoms that are spinning in random directions because there's not sufficiently strong magnetic field applied to them. Then we apply the powerful magnetic field and we actually create the two states. Okay, the beta state, which is in opposition to the applied field, and the alpha state, which is in line with the applied field. Okay? Now, let me ask you a question that will kind of come into play later. Let's theorize a little bit. What happens if I increase the strength of the external field? What does that do to the difference in energies here? It increases it. And that's the difference between really high-cost instruments and low-cost instruments. The high-cost instruments are capable of generating much stronger magnetic fields, so we see better resolution of the NMR because the differences in energies between the spin states is increased. Does that make sense? And we can see it in this diagram. Now, again, resonance occurs then when I apply electromagnetic radiation, and this is a symbol for that, to this separated pair of spin states, and they start resonating back and forth. All right? And that's what the name comes from, nuclear magnetic resonance. Oh, I'm going to pass out my attendance sheet here. I'm going to sign up from now on. Okay. So far, so good. We get our nuclei aligned with or against, and then we apply just the right electromagnetic radiation to give them the resonance. This is the formula that's used. We won't do any calculations with it, that describes the phenomenon we're discussing. The energy difference between the two spin states, which can be made equivalent to the frequency times Planck's constant for the frequency of the light, is equal to a gyromagnetic ratio, gamma, that's different for every kind of nucleus that's magnetically susceptible. Planck's constant times the magnetic field that's applied divided by 2 pi. And so you can see that the energy is directly proportional, between the two states, is directly proportional to the applied magnetic field. And you can see that mathematically here. By the way, in a simple 60 megahertz system, we need to apply a magnetic field of 14,092 Gauss. Okay, is that a pretty strong magnetic field? It really is. What's the magnetic field of the Earth that creates the North and South Pole?
Probably like 10 or 100 maybe?
I don't think it's in here, but it's about 0.5 Gauss. And so the magnetic field of the Earth is not nearly strong enough to make hydrogens go into these aligned or anti-aligned states. Does that make sense? We need to have that kind of a powerful, so it's about 29,000. This is for a simple NMR system. The nicer ones are even much higher in terms of their magnetic field strength. Now, if all protons behave the same, this would be a really expensive proton detector. But fortunately, they don't. The environment, the electromagnetic environment of the protons affects where they resonate. And so we can, and what do I mean by electromagnetic environment?
Light? Or
it refers to the electron environment around them. It turns out that electrons oppose the applied magnetic field. And so if I'm a proton in an electron-rich environment, it's going to take more energy to get me excited. Does that make sense? And so, and that's what creates the powerful aspect of this whole technique. For example, here's a proton, a naked proton, and this is a more powerful instrument. I'm going to apply 70,459 Gauss, and the frequency that will cause that proton to resonate is 300 megahertz. That's out in the radio range, and that will cause this thing to start resonating. All right. Now I put electrons around the proton. I still strike it with 300 megahertz, but it doesn't resonate anymore because the difference in energy has been changed because the electrons are opposing the magnetic field. I said a lot of words in a hurry there.
So are those electrons from surrounding
Yes,
carbons?
on carbons, and it could be oxygens, anything that makes the hydrogen environment electron rich will do this. Now what's happening is the proton, because of the presence of the electrons, which essentially precess in opposition to the applied magnetic field, now my proton's only experiencing 70,458 rather than the applied 70,459. In other words, the effective magnetic field has been reduced a tiny bit by the neighboring electrons. Does that make sense? So now my proton does a signal because the energy difference is different. Okay, because the magnetic field is different. So now I have to increase my magnetic field to 70,460 in order to get the proton to experience 70,459 signals. And our instruments are finely tuned enough so that that difference between 70,459 and 70,460 is detectable. And I can see it as a shift in where the proton is getting excited. Does that make sense? Okay. Now, this is the effect we're talking about. Here's a carbon with hydrogens on it. Here's an oxygen with hydrogen on it. We would expect that this hydrogen attached to oxygen would be less shielded than these hydrogens. For what reason? Yeah, because the oxygen is drawing the electrons away from the hydrogen. And so we would expect the electronic environment around that hydrogen to be weaker or less than we would expect around these hydrogens attached to the carbon. And then, in fact, that's exactly what we see. When a proton is deshielded, it moves on the spectrum to the left, to the downfield side, we call it. That means it's less shielded. The more shielded, the farther to the right in the NMR spectrum. Okay? And this shielding effect allows us to see the different kinds of protons that are present. The number of signals tells us how many different kinds of protons. The location tells us how much shielding or deshielding they're experiencing. The intensity of the signal tells us how many protons are signaling. And just in a simple form, we're getting three kinds of information. Now, something we haven't discussed yet is the splitting pattern, which is probably the most useful information of all. The splitting pattern tells us something about their neighbors. Okay, and so there's just a heck of a lot of information you can derive from an NMR spectrum, as you can see here. Here's how the instrument works. And actually, there's a couple of ways for these things to work. Here's an electromagnet that creates the magnetic field that my sampler here experiences. And the magnet is electronically controlled, so it's very, very fine control of the magnetic field. I also send in a radio signal from a transmitter that's located near the sample and a detector. So I'm zapping the sample with radio frequency, and I've got a detector that's detecting the radio frequency coming through the system. If it absorbs and resonates, I'll see a deflection or a drop in radio frequency passing through the system. So I can tell it's resonating. Does that make sense? Now, I can do it two ways. I can keep the radio frequency constant, 300 megahertz, 60 megahertz, and change the magnetic field to see all of the different kinds of protons. Or I can keep the magnetic field constant and change the radio frequency to detect the different kinds of protons. Both kinds of instruments exist. And it really doesn't matter because we're going to see part per million changes in either the frequency if the magnetic field is held constant, or in the magnetic field if the frequency is held constant. Does that make sense? Very, very small changes, but the instrument is delicate enough, sensitive enough to see those changes. In general, the stronger the applied magnetic field, the more resolution we'll have in seeing the changes. Okay, that's why the big instruments with bigger magnets are more expensive and more useful. This is a big NMR system.